Hi guys, this is Nitin from FTC Team 18172, Uplift Robotics, and this video is going to focus on odometry. This is the first video in a video series all about odometry. We'll cover the basics and progress to encoders and the programming involved. Before we get into this video, we want to thank US Digital for sponsoring our team and this video series. Without them, we would not have been able to create this video. We put some links in the description to their products and particular ones that we use in these videos, so go check out some of their amazing products. Alright, let's start with what specifically odometry is. At its core, odometry is a position tracking system that uses some type of device, usually encoders and FTC, to figure out the distance traveled by the robot from a given starting position. Over time, these measurements can be used to track the movements of the robot and find the relative location of the robot on the field. Okay, so let's say that your robot starts here on the standard 12 by 12 foot playing field. Our robot can do 3 different types of motions from this starting configuration. Our robot can move from left to right or along the x-axis. It can also move up and down along the y-axis, but it can also rotate on its center point, which is the heading of the robot. Using encoders to track all 3 of these motions, the robot can calculate its own position. The more frequent that the robot receives updates from the encoders, the more accurate the position it determines is. This is something called a linear approximation, which you can learn about in a basic introduction to calculus, but I won't go in depth for now. This location information is extremely useful because in the autonomous portion of the game, and sometimes teleop too, the robot can use this information to adjust its position if the wheels lose traction and start to slip, the robot runs into obstacles on the field, or it runs into other robots. More complex algorithms, such as pathfinding and motion profiling, can also be implemented to maximize the efficiency of the robot's movements. We may cover these topics in future videos if you're interested, so let us know in the comment section. You may still be asking, how exactly do you track the robot's movement? Well, the short answer is with encoders, but that doesn't give you the full picture. In FTC, programming is typically done with motor encoders. On all motors in FTC, there's a built-in encoder which tracks the number of rotations of your drivetrain's wheels, for instance. In many cases, this is precise enough to make a consistent autonomous program, and many top teams use motor encoders to create their autonomous. However, there are still some limitations with motor encoders. As you can see here, the robot has run into a wall, and which really can be any obstacle. Although the wheels are still spinning, the robot isn't physically moving. But your robot still thinks that it's moving since the wheels are still spinning. This can also be caused on a smaller scale by wheels losing traction against the field tiles. This can result in less movement than what your robot expects. All of these can build up over time and cause your robot to have an inaccurate location of itself. This is where odometry comes into play, as is commonly known in FTC. Instead of using motor encoders, some teams use wheels that are separate from the motors and use encoders on those wheels to track the position of the robot. Because these dead wheels aren't powered by a motor, they won't spin unless the robot is physically moving. This is still susceptible to slippage, so many teams use springs or rubber band to apply tension on the wheel so that it maintains traction. In order to actually track the rotations, separate encoders from the motors are placed on the same axle as the odometry wheel. The most common ones are the US Digital E4T and S4T optical encoders, along with the Rev through-bore encoders. The typical setup used by most teams is with 3 wheels, 2 in the forwards direction of the robot, and a third perpendicular to the other 2. The average of the 2 forward wheels gives the forwards distance moved, the perpendicular wheel gives the lateral movement of the robot, and rotation is determined by the difference of the 2 forward wheels. As you can see in our team's design, we use this small omni wheel so that the wheels induce less friction for our robot to actually move. We also assembled the E4T encoder here to track the motion of these wheels. There are many resources available from the FTC community if your team is looking to develop odometry, and our team may create more videos in the future on some of the specifics. In our next video, we'll be going over the details of the E4T optical encoder. Once again, thanks to US Digital for sponsoring our team and this video series, so be sure to support them by checking out some of their products. If you have any questions about odometry, let us know by contacting our team through our social media in the description or by leaving a comment down below. Thanks for watching and stay tuned for more videos.